In this video, we will discuss Gay-Lussac's law. Game ka na ba? Tara na! Gay-Lussac's law states that the pressure of a certain amount of gas is directly proportional to its absolute temperature at constant volume. This is named after Gay-Lussac, who studied the volume-temperature relationships of gases in 1802. Sometimes this law is also known as the Montan's law, after Guillermo Montan, who in 1703 built a gas thermometer based on his theory that the pressure of a gas related to its temperature. What does directly proportional mean? It means that when pressure increased, temperature will increase, or when pressure decreased, temperature will also decrease.
The relationship among pressure and temperature are constant volume can be mathematically representative by an equation. Here's the mathematically representation of Gay-Lussac. P1 over T1 is equal to P1 over T2, or P1 T2 is equal to P2 T1, where P1 is the initial pressure, P2 is the new pressure, T1 is the initial temperature, T2 is the new temperature.
The first step is to use the Gaussian method and then find the given, which will be pressure 1 is equals to 4.0 atmosphere, temperature 1 is equals to 27 degrees Celsius, and then temperature 2 is equals to 402 degrees Celsius, and then P2 is equals to question mark, which will be our required because it is what we're going to find in this sample problem. Now let's proceed with the equation, which will be pressure 1 times temperature 2 is equals to pressure 2 is equals to temperature 1. And let's proceed to solving of the problem, which will be pressure 2 is equals to pressure 1 times temperature 2 over temperature 1. Now, how did we get this formula? Keep in mind that pressure 2 is the one that we're looking for, so therefore, we need to solve the equation that we got from the formula itself. Pressure 1 times temperature 2 over temperature 1. Now, P2 is the one that we're looking for, and it is beside T1, which will automatically be the one in the bottom. And now, let's change the units to its given, which will be 4.0 atmosphere times 665 Kelvin. Now, how did we get this? Another thing to remember is that when converting degrees Celsius to Kelvin, you just have to add 273 to any degree Celsius. 402 degrees Celsius plus 273 Kelvin is equals to 665 Kelvin. And 27 degrees Celsius plus 273 Kelvin is equals to 300 Kelvin. Now, let's proceed with the solving. 4.0 atmosphere times 675 Kelvin is equals to 2,700 atmosphere, and we will be left with the Kelvin, or the unit itself, over 300 Kelvin. Now, we can cancel this out and then proceed with solving it. 2,700 atmosphere divided by 300 is equals to 9 atmosphere. And that will be our final answer in this sample problem. And now that we have our final answer, we need to remember one last thing. And that is, pressure will always be and is directly proportional to temperature, and vice versa. So, if the temperature increase, the pressure will increase. And if the pressure increase, the temperature will increase. And in this problem, we find that from T1 to T2, the temperature increased.
Experiment on Gay-Lussac's law.
As previously stated by Ms. Crisel, Gay-Lussac's law states that pressure and temperature are directly proportional at a constant volume. This means that as pressure is increased, the temperature increases and vice versa.
Materials that we need for this experiment are 2 candles, a beaker or glass, some water, a shallow dish, food coloring, and a beauty lighter.
Although the experiment that we will do is very hazardous. It is always a good idea that we wear our safety goggles, a lab coat, or an apron to provide protection from any accidents such as spills and splashes.
And also, for our young audiences, always make sure to have adult supervision and handle reading in time.
So in this experiment, the first thing we are going to do is fill our swallow dish with water, and in order to make it easier to see, we will add a bit of food coloring to the water.
For the next step is take your candle and place them in the center of the water. And light them up using butane lighter. And finally, for our last step is make your glass and place it on the top of the candle.
You'll notice the candle flames will get smaller and smaller until they are extinguished. If you watch closely, you will see that the water level underneath our jar begins to rise as the candles fade away. The water level will continue to rise for a short time after the candle has been fully extinguished. You will also notice that the water underneath the jar is much higher than the water in the plastic container. In our experiment, our jar is filled with gaseous air molecules. The energy from our flames transfers to the air molecules, exciting them by raising their temperature. When the air molecules in our jar are excited, they try and spread further apart. But because our jar would not expand like a balloon, the volume of space our air molecules can take up is limited. As they try and expand in volume, the air molecules press harder and harder against the walls of our jar and the water at its base. This increase in air pressure under our jar causes the water level under it to be pushed lower than the water level outside of it. The higher the temperature or the more energy the air molecules get, the more pressure will be created under our jar. Once the flame is extinguished, the air molecules under our jar begin to cool off, dropping temperature and losing their excitement. This causes the amount of pressure our air molecules exerting on the sides of our jar and the water at its base to drop as the pressure drops. The water in our plastic container is pulled into our jar, raising the water level under the jar, equalizing its pressure. By changing the temperature under our jar, we can clearly see the directly proportional relationship between the temperature and pressure of an ideal gas. This relationship is known as Gay-Lussac's law.